Right, hello. Please look at this monitor, and I thought I will explain to you a little more about how this product has come about. So, if you look at the few samples that I brought here, as I explained to you, this one is a cup, so that I can have tea as and when I want. Now, this is typically one of our nice what they call pet projects which we can attempt. It is a little technical and a little personal, and you can configure it as you like. So, traditionally if you were to heat tea, you had to buy one of these so called USB heaters. So, we have a small issue with it. I do not know whether I should call it an issue or a technicality which you need to work around and so on. One of them is, typically any one of these devices can give you 500 milliamps at 5 volts. So, if you take 500 milliamps at 5 volts, it will give you only 2.5 watts. So, if you have an already brewed ready made what you call tea, you can keep it on top of it and keep it warm a little longer than this thing. Now, if you see here, what we have inside this is some device which which has, I do not know what you can call it, a heater inside, and it makes things easy. Now, the challenge which one of my students took is, sir, I want to make tea, I do not want to keep warm tea, meaning he has a typical what you call coffee or tea brewing cup here, and then he wanted to put hot water in it. One way of doing it is have a kettle outside and then put it inside. Alternatively, instead of carrying all this, is there a way I can make tea directly? And now we come to the important point. If the ambient typically for us, luckily the ambient is around 30 degrees, for you to make any useful tea you need to step it up by 60 degrees, at least to make it up to 90 degrees. And if you can steep the tea at 90 degrees for the duration you want, you get very nice good tea. Now comes the question saying we have to do some heat load calculation, saying how much of wattage do you require here to warm this cup. So, these things, as I told you, typically this takes only 500 milliamperes and 5 volts, it will come to 2.5 watts. They are not enough of current for us to heat the tea to make heat water to make tea. So, the challenge was how to have a heater which can take more current. If you go to the internet and check, there is something called the water heater calculations. So, typically it says find out the amount of liters of water you want to do into the temperature rise you want, multiplied by 4 divided by 3142. That is a standard formula that directly gives you the heater in kilowatts. So, if you play around, and typically at a time say if you need to fill this, you need to make 250 or 300 ml, but if I just need to have tea whenever I want, I can probably manage. This is a 150 ml cup, maybe I can even manage with a 100 ml cup. So, typically if you want to heat 100 ml through around 40 or 50 degrees centigrade, it requires at least a heater which is 10 to 15 watts. So, I need 2 amps, and it is not correct to say I will take a parallel USB thing and all that is fine if you have a huge what do you call power supply. If you are running a small laptop like mine, you cannot afford to discharge the main battery. So, the here came saying what do we do now? I need to heat the water quickly, but I had to use only one what do you call USB port. So, if you can kindly look at this the monitor. So, one of the students came out with a big this thing is saying, sir, it is obvious whenever you are talking about any what you call battery or anything, you are talking about a, you see here I have one of the smallest cutest what do you call this USB stick. Other than lighting itself, I do not see it giving too much of, see it has a green light and a red light. Other than that, oh it has a blue light, I am sorry, blue light and a red light. Other than that, no, it does not seem to do any good. Thing is, inside I have a battery which is typically 2500 or 2.5 ampere hours. So, there is an hour feature also. So, I have 5 volts, actually in this case it is 3.7. So, if I take 5 volts, it will come to 5 into typically 1.5 amperes hours also. So, 5 into 1.5, or if I take 5 into 2, I have 10 watt hours of this. So, 1 hour it can give me 10 watts, is it not? Now, how do I play around with this hours thing? So, what was decided is nothing prevents us from charging a device continuously like this. So, say I have a I am sorry, I have this beautiful device, why do not I pack it with batteries and I connect it to my usual USB output, and then continuously it keeps charging, and once the battery is charged I can go around playing with it. So, 2-3 different strategies have been made. One of that is take all the energy and store it in a battery. Secondly, make sure that no heat is lost, you insulate it, and thirdly you need to do some temperature control. Some of you would have seen these devices which we use all over the place, especially in wherever we have mosquitoes. We need this is a mosquito mat thing. This one uses a bottle and then there is a ring heater all around, and then I can go around trying to can I use that piece which is inside. So, after having searched everywhere, we got this thing. This one is a heater which is built into flat mosquito pads. So, at the bottom we have a heater and the whole thing has been what do you call put together. Typically the rating of this is about 5 to 7 watts. So, we did an experiment on this saying is 5 to 7 watts, okay, and then this one is taken from a insulin, it is a human mixed means it is a human insulin thing which comes, and we made a heat sink, made it here, and then afterwards I now it is actually in reverse, it has a cover, this whole thing is placed on the cover like this, and I have a AC inlet here, I give a AC inlet and I keep it covered and measure the temperature. Then to our surprise we found the 7 watts, if you leave it for around 2 or 3 hours and insulate it fully, does reach a temperature what we want. You understand, no? It looks a little too empirical and trial and error. Reality is you can also calculate these things. So, that was the starting point for the this thing. Now, coming back to my product there, if you have a look at my product, it has several interesting things. One of them is there is a insulation all around, and second thing is again I was talking to you about. Sir, show this what you call thing here. This is a beautiful battery bank, and then I have all these cells here. All these cells are 3.7 volts. Nominally, if you give 4 volts, they start charging. So, all this have been packed into a box here. So, I have 10 of these cells nicely packed into a box, and even if I give 5 volts, it does not matter. I have a charger here. This one is a 5 volt 2.5 amps charger. So, I charge the batteries as I want, or I can even use the laptop power supply. If the laptop is being charged on one side, continuously it can charge my battery. So, energy storage has been achieved by using external cells. These external cells, depending on your size and all that, can come. I do not have the what you call, sadly no connection to the internet has been lost. I thought it will be there now. If you go to the several what you call sites, we have positive temperature coefficient thermistors on sale, and the advantage of the thermistor being, if you have on the x axis the what do you call, I have forgotten what it is, yeah. Okay. On vertical you have a temperature, and this case no some other thing I am not able to recollect. The advantage is, irrespective of the time and current around us, no, until the temperature reaches that set point, usually 70 degrees centigrade, that has a one slope, and the moment the surface temperature reaches that set temperature, they are usually made for 120 degrees centigrade. For some reason no, we need that, suddenly that slope goes up at all. This dual slope is the positive temperature coefficient. So, it is almost self regulating. So, the current in the initial stage, what takes around maybe 2 or 3 amps, will finally come down to less than that rated 300 or 250 milliamps. So, if you can get a PTC thermistor and mount it on one of these things, we can happily have a water heater which can heat temperature from the bottom. Now, the second point is, this is traditionally a cup, except that this is insulated by a double wall. It is a double walled cup. It is possible for us to do something. One of the easiest thing is to probably drill a hole and fill it up with more water, meaning I fill a hole here, fill it up with more water, then it is up to 100 degrees it can easily do. And then if I have a way of probably sealing the hole, it will be a little like my pressure cooker, which the temperature can rise above that, then inside it heats this, but little risky business. Other option is, go and look for a simple stainless steel cup which is not insulated and place it on that. Now, heating this has been solved to one problem. I have a temperature controlled PTC thermistor plate which can be heated up. In this case, only for a simple demonstration, I will showing you this what is built into this thing. These are all made for 350 milliamps and 5 volts, which will come about 1.5 watts, just about enough to keep things warm. And then I now replace it with something which is a 10 watt thing, saying it takes 2 to 3 amps at the bottom, but PTC thermistor. Further, I can have in fact a control by which I can even increase it to, maybe depending on the storage capacity available, maybe I can increase it to even 5 watts. If I have 5 amps into 10, no, it will come to 50 watts. So, I can heat it nicely. This is where the next generation thing has been taken, saying I have got the heating problem solved. Heating problem is solved well. Next, I have got the energy storage problem solved. Next thing is saying I need to insulate it. So, if you kindly look at my what you call the demonstration, you see here what these people have done is, they have insulated this whole thing all around, and even if you see the what you call the taper that is there. So, probably I need to get some cup which is a tapered, so that it makes a even firm contact everywhere here. So, I have something in the base, and all around also it is heated to prevent from various what you call thermals and all that. A little bit of trick also has been used here, saying that heater is spread all around like this. So, naturally it has a tendency to make the top layer little warm. So, you can always drink, keep it back there. When you keep it back there, it keeps increasing in its what you call the top layer continues to get hot. So, it does not matter what is the input you give. Input could be stored all over the thing, and then you keep your cup and probably close it. Keep it covered, you have another insulated cup, and the volume inside the cup gets hot. So, if you have water, water does not evaporate very well when it is around 60 degrees centigrade or so. Only if it reaches 90-95, evaporation starts. So, keep it normally, constantly keep it at 50 or 60 degrees centigrade. Whenever you want to make tea, flip a switch, let it come up to the maximum typically at 90 degrees, and the moment you have a 90 degrees and there are two switches in, something which indicates the temperature, put either tea leaves or put a tea bag and then steep it for whatever time you want and then take it off. Now, we have a beautiful what you call arrangement by which I have a tea warmer which is also tea maker, and you see life is very very easy and convenient for me. And the same water, if I can take it in a water and do something, I can even put it in this teacup device which I have here. So, when we went and got this was not sitting comfortably on this, you see here, because of the what you call sort of standardization, we need to offset it a little. So, my students have been good enough to make an adapter for me. So, the adapter sits on this, now I keep it here. So, probably I will heat water, or if the water is heated I put it inside, it comes and I have a nice beautiful valve here, and I use it like this, and these people have given me a very convenient what you call coaster also. So, I have a beautiful thing here, you see here, it sits conveniently here, and maybe I can even keep it here and do whatever I want with it, you see here. So, I have a beautiful teacup, warmer, tea maker, coffee maker. Maybe this is where let me be a little careful. If I can replace that base with a thermoelectric what you call plate, maybe I can have a chiller also. So, some people prefer having water at room temperature, and what you call most fruit drinks are probably taken at room temperature. However, if you are one of those persons who would like to take them a little cooler, maybe take it around 20 degrees centigrade, because it does feel a little more refreshing at that. And I should not mention things like wine and all that. No, so those things, if you want to chill them, by converting the bottom PTC thermistor and removing it and replacing by a Peltier element, it is possible for us to make it into a cooler device also. Now, if you come back to my computer, it is just a what you call, it is nothing, kindly, it is just nothing, it is not a big deal, as I say, no, it is not rocket science. So, one of the easiest way is, already in most of the geometry primitives we have things like these cones, pyramids, all these things are already built inside. So, center of base of the pyramid, yeah, cone, okay, base of cone. See, I have, actually there are better ways of building. See here, I have a cone already in this. How about the angle and all that? You just need to go to the shop and find out which one of these things has a better thing for you. Now, I see what best I can do. Is there a way of making into that product which I have shown you? The easiest is obviously to cut this. Okay. So, I have here a surface which is a cutting plane. I take this object and I try to trim it off. See, I have got something here which is, I think, if you remember in one of those pictures, he has shown you, be careful about the thing. This is a shortcoming of this particular program. This is not a universal program, not a universal thing. In this case, this being actually a surface modeler, NURBS based surface modeler, it does not do, if you do trimming, it will end up with this. Logically, I should have done a normal regular Boolean operation. So, I will go back and do a Boolean operation and show you how stuff is easier to do with that. See, here I have this. Now, I take a solid and cut off the material at the bottom. Hey, what happened? Oh, oh, very good, very good. It was not sitting here properly. See, here it is only sitting in a halfway. Serves me right. Now I see, I will try to, oh, it is not done properly, sorry, it is a bomb. I make a proper solid. Take it down. Now do a Boolean. So, here I have a reasonably well done cup and it is closed on both the thing, okay. Top and bottom sides, both of them are closed. Nothing, I am just trying to create a hollow cup. So, what I do is now make it what do you call a hollow cup by probably copying on itself again. And see, got it. I have a nice hollow surface here. Now, this exactly is not exactly the cup which I am looking for. However, this is the item no, which now inside this I need to make sure that I put grooves so that a heater wire also can be put. This heater wire need not be of the PTC type which I was talking to you about. The PTC what do you call the thing can sit inside this bottom, okay. And I am happy that you have thought about it. What about conduction? Yes, we need to have conduction. So, it is likely that the PTC thermistor what we have now will actually heat up a plate at the bottom. So, what I do is I will remove this bottom and try to make a small cylindrical plate here. I make a cylinder here by see, I have a cup which has a opening inside which is quite a lot like this small thing which I have shown you here. Seen this no. Now, this base portion have to make some arrangement by which a conductive what you call aluminum plate or something else which sits a lot like this. You have seen this here. Okay. Two things here, one is I need to make it circular, I need to make some arrangements by which I clamp this thermistor onto it. So, since this exercise is a little more to do with rapid prototyping and not so much to do with the other details, I will gloss over the details. I will just assume we have a nice circular plate for a see I have a plate there which for the present I will assume that it is a what you call nice thing which does all the heating and all that, and it is possible for me by various operations to maybe even make a step. I can make the step by adding another cylinder on top of it and which sits neatly at the bottom. Oh, I will use this circle, take it down here and see whether I can make a solid out of it. This forms a thermal bridge. See there, I have a small plate which goes through this plastic, and one or two features you will notice is it is not touching it anywhere, so that the heat is not directly affecting the plastic. I have left a small gap. Here I would like to give your show your notice to any insulation. All insulation works on the basis of trapped air. So, if I make sufficient caution such that the plate does not automatically touch the walls, that is enough of an insulation. Further, if I want, I can always put polyurethane foam. Polyurethane foam can easily withstand 150 to 200 degrees centigrade. So, I make a ring of polyurethane foam and just push it inside. This heater will continue to heat the bottom surface of my cup, and inside of that I can have one more metallic cone in which heater wire is put. The only thing is the metallic cone, that heater wire may be only of the order of maybe less than a watt. So, I can have 500 into 100 milliamps, maybe 0.5 watt. So, if I have 0.5 watt, that is enough to keep it the edge very much warm, and further if I want to heat it and all that, I need to work more on it, but this is the starting point. Now, having this, now we come to the other equally important things.